sinking in. It does take a while. It does take a few rereadings, maybe of certain sections where you're trying to incorporate, because for many of you, if not all of you, this is very new. This is brand spanking new information, probably that, you weren't exposed to in college, like A&P, RadPro. They have some similarities, but not likely, unless you took quanta physics in college, this is probably a little bit more abstract, okay, right now. But as you start to put the pieces together, as you start to fully incorporate what is what and what does what do, it starts to make sense as we venture off into the next chapter.
Miss Laura, a few of the students are having trouble logging in. They said that it's telling them that the WebEx code was canceled for them. Amy and Sun are texting right now.
Really?
Yeah, I sent them the code again. That's the only code that worked, even from Unity. So they're having trouble.
Okay, so let me go back. Let me see. Forward.
Amy said that the passcode is incorrect that we're sending her, but it's the only passcode that we have.
PRE Mondays and Wednesdays. I'm sending it back again.
Miss Laura, for me, I had 2 links, and the first link said that the class was canceled.
Okay.
I just sent Amy the other link that worked for me. But for me, it shows 2.
Really?
Mm-hmm.
Was it the previous one that I had?
Yeah.
The previous PRE class?
Yeah.
Because I made a change. I ended up making a time change on it. And so that's probably what is showing.
Yeah, because the one that actually shows that it's deleted because it was changed, that's the one that worked for me.
Really? That's weird.
And that happened to me last class too.
That happened to me last class too. I had to go back through my deletes to try to find one that would work.
Okay, so I just re-forwarded the series back to you. Let me see when you guys try that one. Let me know if that link works for you. Okay, if not, then I'll just take off all of the reoccurrence and just do what we used to, just do invites weekly. Are you having any problems with any other courses with Mr. Donahue's or?
Mr. Donahue just sends us like a link to it that we click on every day. Like he doesn't actually send us like the WebEx code one. He'll send us like a URL that we'll just type in and it'll send us right to us.
So, but is it a reoccurrence?
No.
Is it a reoccurrence? No. Okay. I think we're all on. So yeah, I just sent you I forwarded the series over to you and just let me know what happens with that. Okay, and then I'll be sending the one for Friday, since Friday's changing. Any other questions about the getting on the WebEx? No? Have any questions in general? It says it didn't go. I'll have to look back and see why it didn't go. Write that on my to-do list. Well, that's it.
Ms. Lara, question is answered. I was wondering if we could do like an overall, like a class, like if you could ask random questions, and that way we could, if it helps me when you ask questions, because even if I don't answer them like directly, I know if I'm understanding, if you're just kind of asking different things.
I don't mind asking a few, but I won't be doing that the entire class time. Because I think at this point, we need to kind of know where we're struggling. So if I went back and let's just say I did a quick synopsis of what we've talked about. So if I went back and I gave you something like this, let's see, share. And I started to say, well, name the parts of the anode. That's a question, right? And then if you start to say, well, first, let's start at the beginning. Where did we start at the beginning when we opened up this chapter? And this is part of engagement. So I don't want to stare at you, and I don't want you just staring at me. So this is your review. So what did we open up the entire chapter with? We started talking about protective housing. Explain to me, as Betty, what is the purpose of the protective housing?
To ensure that it doesn't, like, for the heat, like, it has a mechanical support, electrical insulator, thermal cushion. It just makes sure it doesn't overheat the tube.
Okay,
like,
so let me ask you this question. Yes, you're absolutely correct. That is the function of the protective housing. But true or false? The tube sits inside of the protective housing.
The tube?
True, the tube is.
They are two separate components, right?
Mhm.
Yes? Make sense?
Yes, ma'am.
They are two separate components. The protective housing is not an AKA for the X-ray tube.
Mhm.
So the purpose of the X-ray tube, as you said, it provides insulation, it provides mechanical support for the X-ray tube, it protects the X-ray tube, it also has the oil. What's the purpose of the oil, Maricela?
To dissipate the heat.
Okay, good. Where is the heat being generated from, Tracy?
The X-ray protection from the filament being burned off.
Tracy, did you hear me? Where is the heat being generated from?
The filament.
Okay, let me be a little bit more specific. The heat at the filament is causing an emission. That is not the heat that is being dissipated by the oil. I see where you're going with that, but that is not, heat is not the same here. Where is the heat being generated from, Amy?
Was it the anode?
What about the anode? What's happening at the anode that is generating heat?
The electrons are being hit into the disk, and that's what's causing the heat to happen.
Correct. Absolutely. So the heat that the oil that is bathing inside of the protective housing is being generated when the electrons collide at the target, not thermionic emission. Good. What else does the protective housing do, Daniel? We talked about the oil. It also supports a fan. Tell me about the fan. We'll come back to you, Daniel. Isaias, help him out.
It's going to be dissipate heats.
It is going to dissipate heat. So we have two items, two factors that are going to help us dissipate heat from the X-ray tube. That is going to be one, the oil that sits inside of the protective housing. So you have the house. Inside, you'll find oil. Inside of that, submerged in that oil, you will have an X-ray tube. Got it? And there's also a connection for the collimator assembly of the protective housing, as well as a fan area. Does that make sense? So the protective housing has an area for the X-ray tube to sit in. It contains oil, not inside the X-ray tube, but outside of the X-ray tube. It has a space for the collimator assembly, and it also has a space for the fan. We dissipate heat by way of the fan and the oil. Make sense? Yes? Perfect. Any questions about the protective housing?
Doesn't the protective housing also protect against leakage?
Yes, absolutely. So tell me, where does the leakage come from, Jalisha?
Isn't it from when the X-rays are produced? Some of them scatter off.
They do. I like the word scatter because scatter is going to mean a lot of things for us later. So when electrons, we know that the electrons are flowing over in the tube current, and we have aimed the tube current to make impact at the focal spot, the actual focal spot of the rotating anode focal tract. The electrons that are not, the electrons that hit outside of that area and still manage to generate X-rays is where the leakage radiation comes from. So the X-rays that are not in the effective focal spot that don't bombard at the actual focal spot, they maybe bombard outside at the actual focal spot, can bounce back, or what you say scatter, into different directions. And that is considered leakage radiation. The protective housing is lead lined for that purpose to absorb those photons. What is the measurement? What is the standard requirement that that the protective housing is protecting individuals from leakage radiation efficiently? Shannon.
100 milliroentgens per hour at a distance of 1 meter.
Perfect. Absolutely perfect. And that is for leakage radiation. Got it? Yes? Perfect. Good. Go ahead. Yeah, anybody have a question about that? All right. Good. Oh, and the protective housing has an area for those high tension cables, right? Because we're going to be dealing with a lot of high energy electricity. Perfect. Okay. So let's move on to the X-ray tube envelope. Javier, tell me about them.
The envelope, is that right?
The envelope. We have to type the envelope.
It keeps the electric arcs from staying.
Which one is that one? Which one helps prevent electric arcing?
The metal piece?
Is that the metal one or the glass one?
Metal.
The metal one. What does the glass one do? What is the advantage of the glass envelope?
The glass one was for heat.
Good.
More heat resistant.
There you go. Very good. All right. Perfect. Let's see. That was pretty much it of the envelopes, right? Didn't really talk about anything else. But the envelopes also, whether they're metal or glass, maintain what kind of condition inside of the tube loop?
A vacuum.
A vacuum tube. What's the purpose of that, Luke?
To keep the keep the electrons from anything else.
From hitting or colliding, like bumper cars, with anything else. We definitely don't want any air molecules to be in the way, right? Good. Perfect. So the envelope maintains a vacuum seal around the X-ray tube. If the tube cracks, the glass cracks, it has to be fully replaced, right? Any components inside of the X-ray tube breaks, the whole entire X-ray tube must be replaced. Good? Fair enough? Any questions about the X-ray envelope? Perfect. All right. So there are two phases to get production of X-rays to happen, there are two phases controlled by us at the operator console. Well, we only control the exposure switch. Once we apply pressure onto the exposure switch, we're not clicking on it. We are having to apply pressure. And eventually we'll learn that that's called the dead man switch. But we have to apply pressure. There are two phases. What is likely going to happen in the first phase? In the first phase, they're described in two separate words. Can anyone tell me what the first phase is described as?
Standby?
Like the warm-up phase, is that what you're talking about?
It is a warm-up phase or a prep phase. But what is also happening in the prep phase, and that's how you should probably remember it, first phase, prep phase, we are prepping the anode. We have to achieve, Shannon, as to how high RPMs. How high do we have to achieve the RPMs of our spinning or rotating anode?
3,400.
Karen? Oh, I'm sorry. Go ahead.
You mean 3,400?
3,400 RPMs, right? So in the prep phase or the first phase, it's also referred to as the mechanical, because now we have to prompt our induction motor. Who can tell me about the process of the induction motor?
It turns the rotor in the I know it turns the disc.
It does. So the rotor, the stem, and the anode disc are one piece. There's one piece, different parts, and different types of material construction. Okay? So where is the electricity applied to? The stator or the rotor? Jessley.
Is it stator?
It is stator because the stator stays outside. So it is outside and it is going to receive electricity. So when the stator receives electricity, remember, there are magnet pairs situated around the stators. The stator is going to be around the rotor. But remember, the rotor is inside and the stator is outside. Here is the rotor. The stator would be out here. Make sense? Good. So if we apply electricity to the stator, how do we get the rotor to turn? That is called the induction motor. They don't connect. They're not connected, right? But how do I get the rotor to move? By applying electricity. By applying electricity, where is my image? By applying electricity to these pairs of magnets. Once we apply a pair to the magnet, the iron rotor is going to align itself to those magnets, north and south pole. When we activate the other pairs in sequence, in synchronous fashion, we're changing the direction of the north and south pole inside of the iron. Make sense? If we keep doing it in sequence fashion, fast, we're getting that rotor to turn. Make sense? As fast as 3,400 RPMs. That is the process of induction motor. We are electrifying or applying electricity to the stator, causing magnets right? To activate and the rotor, the iron of the rotor to align its north and south pole of metal. And that's what's getting it to turn. Good? Everyone understand? Anyone have any questions? So I did mention that the iron, it's an iron rotor for the purpose of having the magnetic attraction of the stator, the magnets in the stator. Make sense? Good. Perfect, perfect. So in the prep phase, we are activating the induction motor. We are now spinning our anode disc. Make sense? Good. Also at the prep phase, we are now heating up the filament. Tell me about that, Chibu. Tell me about the filament heating.
When the filament heating, then it will attract the electrons to the.
It will boil off. The words that are being used will boil off. Perfect. Good.
So then.
And what do we call that process?
Thermionic emission.
There you go. Perfect. Emission, because the electrons are being boiled off. Why do we use tungsten, Ruth, in the filament?
Because the tungsten has a high thermic, because the tungsten is very high on melting point.
It's very difficult to melt it, isn't it? So it can withstand high temperatures because it's very difficult to melt it. Okay? If it was easily melted, it wouldn't do anything. The filament would lose its structure. And we need the structure, right? Good, perfect. What is the filament mixed with? Tungsten and what, Naomi?
Tungsten and, is this one have rhenium?
Yeah, I wish I could have a way to say,
what is it?
I don't know. I can only think of TT filament. It's the TT filament. I don't know. It's the thorium. Thorium and tungsten. TT filament. Okay?
What's the answer?
So, it sounds kind of weird, but that's probably the best way to remember it. Okay? So tungsten with thorium. Rhenium is where the electrons are going to bombard. Question? No? No? Okay, good. All right. So phase one, now we have electrons. And they're sitting inside of the focusing cup, Stephanie. But they're not just sitting inside of the focusing cup. They are creating a cloud of electrons. What is that cloud called?
Space charge effect.
I'm sorry, I couldn't hear you.
It's okay. What is the cloud called? The cloud of electrons. What do we call that?
It's the space charge.
It is? Good. So, then we have phase two. Phase two is called the exposure phase. We are still pressing that button. And when you guys go back into clinic, when you're pressing the button, listen for the mechanical phase. You're going to hear, that is your rotating anode getting up to speed. Okay? We know that we're starting to activate the heating element for thermionic emission. We know that we're doing that. Once we hit the exposure phase, now we're sending those electrons over. We're now applying kinetic energy. How are we applying or generating a kinetic energy of these electrons? John, help me out.
We are putting a positive charge in the anode.
We're putting a positive charge in the anode. We are making that anode oh so attractive so those electrons will flow on over, speed on over. What do we call that flow, Wani?
Two charge.
What do we call this flow of electrons?
Two current.
Current.
Current. This is our X-ray tube current. Perfect. Good. And it is the flow of the electrons. Okay? So now that the electrons are flowing over, they are going to collide with what, Duan?
The anode. They have to roughly stop at the anode.
All right, can you repeat again?
The electrons are flowing over. They are going to collide with what?
What is
it going to hit? What is it going to bombard?
It's like blow the electron from the cathode to anode and.
Mm-hmm. Where are we going to make these wonderful X-rays? And what section of the focal tract? Help her out, Amy.
Is it the target window?
Not the window, but you have target correct. The target where the electrons will collide, right, is at the actual focal spot. Because actually electrons are interacting. With that, we have the line focus principle. What does the line focus principle tell us?
That if you angle the target anode, it'll allow for a smaller effective focal spot.
Is that what we want? Is that ideal?
Yes.
We want a larger actual focal spot so we have more room for those electrons to collide with. But we want a smaller effective focal spot so that we can funnel those X-rays out of the window or the port of the X-ray. Make sense? So the line focus principle is with angling the anode target. Okay? So if you take your racetrack and you kind of angle it a little bit, that is the concept of the line focus principle. Because we are trying to direct our X-rays out of the window or port of the X-ray tube. Make sense? Good. It's kind of like aiming. It's like aiming, just like this light picture that I showed you. We're aiming and angling the mirror to get the X-rays out of the port window. So we know where to aim our X-ray tube. We know that if we have our tube, X-rays are coming out this way. They're not going out this way, they're not going out this way, or they're not going out this way. We are able to aim our central ray. We are able to aim our central ray in the direction where we need it to. Make sense? Good. What is the anode heel effect? Daniel, I'm back to you. What is the anode heel effect?
It's the intensity of the X-ray beam.
What does intensity mean? Use the word that I'm going to forever say for the 2 years that you know me, intensity.
The amount of energy?
The amount of X-rays, not energy. The amount of X-rays. So if we counted how many X-ray for how many photons, particles, are in this beam, that is called intensity. It's the quantity. We know that your definition said energy. I kind of want you to just subtract energy because it is going to make more sense later why I want you to subtract energy right now. It is the quantity. So if I said on the anode side, because of this molybdenum heel, can you guys see my screen? This molybdenum heel is absorbing those photons. We would have less photons on the anode side. We would have more photons on the cathode side, saying, AKA, we have a higher intensity on the cathode side and a lower intensity on the anode side. So when we have this effect, we have to know how to overcome it. If we have a tissue difference that is thinner versus thicker, we always want to aim our cathode side to the thicker tissue where there's more X-rays to penetrate. Make sense? Yes? Awesome. Is this review helping you? Are you tying it in together? Yes? Perfect. So let me go back to my stars. It says the smaller the effective focal spot, the better the image quality. That is true. We just said the line focus principle allows us to angle the target so that we can have a larger actual focal spot with a smaller effective focal spot. So the effective focal spot is completely dependent on the angle dimensions of the anode target. Make sense? So the smaller the angle of the anode target, the smaller the effective focal spot. Roughly, we have an angulation of about 12 degrees, between 7 to 18 degrees. Please remember that. So roughly, to get a small effective focal spot and a useful one, why do we want a small effective focal spot again, Aurora? It's okay. No. We want a smaller effective focal spot because we want better image quality. So we're always chasing the smaller effective focal spot because we're always trying to improve image quality, right? And when we say image quality, we know that we are talking about the image. Make sense? So what happens in here plays a big role of here. Okay? Good. So, what else? The principles of operation. I gave you a recipe how to make X-rays. We need an electron source. We need to get those electrons to move. And we need to combine, it's okay. We need to also collide, abruptly stop those electrons in motion. So we are having a conversion of energy, right? So electricity is coming in. It is supplying electricity to our filament, right? Hold on, excuse me 1 second. Okay, sorry, they're probably banging back here. Okay, so electricity is coming in. This is a tungsten with thorium filament. The electrons from the tungsten atoms are boiling off. Okay? So we converted electrical current to thermionic emission. These electrons are going to eventually flow. So we have converted electricity to thermionic emission to current, right? Electrons are going to flow. That current is off of kinetic energy. Once these electrons flow and collide with the anode, there is another conversion. It's either their kinetic energy of the electrons will either be converted to heat, which is most likely, or to X-ray. So there is a conversion of energy along the way. Because energy is not created nor destroyed, it turns into something else or converted. Make sense? So, when we talk about tungsten, we're talking about electrons. We talk about the reason why this element is chosen is because it has a high melting point. So the electrons that are orbiting in this tungsten atom are the ones that are being boiled off. Make sense? We also said that the X-ray tube is a diode. Electricity is coming in and electricity is going out. So the electrons that did not convert will continue out from the anode side. Any questions about that? Making more sense? Is it flowing? We understand what these electrons are for. So when we go back and we look at the one with the stars, the three things needed to produce X-rays, we need those filament electrons. We have to, this word right here, these words are fancy, but this is basically saying I need to attract those negative electrons and get them to move. So when we apply electricity to our anode or charge the positive anode, the electrons will naturally be attracted to the anode to move, and that is the kinetic energy, right? When electrons are in motion, they are flowing. We call that tube current, correct? And when the electrons collide with our focal spot, that's what's going to happen, the interaction. Either heat is going to be converted or X-ray is going to be converted. If nothing gets converted, it will continue on its merry way out to the electrical circuit. Okay? Any questions? Sure.
Yeah. And the last class, I don't know if I wrote it down right or misunderstood or understood it right. I think you said that kinetic energy was kind of the same as electrical current, or
the kinetic energy. Okay, so electrons are flowing, right? So when electrons flow, that is electrical current. You're talking electricity. It is electrons that are flowing. So what I'm saying here is tube current. If you define that, what does that mean? Electrons in motion. If electrons are in motion, what kind of energy do they possess? If electrons are in motion, what kind of energy do they possess?
Kinetic energy.
Beautiful. Kinetic energy.
Miss Lara.
Uh-huh.
So when you say cloud, the cloud is like the space charge, and it happens in the focusing cup. And the thermionic emission is happen in the filament.
Yes.
Okay.
So the filament gets super hot, right? Kind of like your light bulb. What happens when your light bulb? Your light bulb, the filament, that little filament, it's glowing, right? It's hot. That's what's giving you emitting light. Here, because this filament gets so hot, high temperatures, it's boiling off the electrons from the tungsten atoms that make up the filament. Okay? So we talked about materials. What is the focal track made of? Marisela.
Tungsten with splash uranium.
There we go. I love it. I love the splash. Sounds like a bar. Anyways, but no, that came out wrong. Anyways, what is the area around the focal track made of, Jaleisha?
I'm not 100% sure.
It's okay. It's okay. So if you think of a racing track, and you think of your high school track, and it's got grass on the inside where they play football, and then they got grass on the outside, right? You think of that? If I were to say the grassy area of the anode, because this is what an anode looks like. And it's kind of difficult to see. But this is an old anode. Can everyone see it? Oh, let me see. Where am I? Where am I? I don't see myself. Okay, so here we have it. When you really think, there is an area around that is called the focal track. Its texture is very difficult to see. Its texture is different. Do you see that? Smooth area. This is called the focal track. This is the tungsten and the rhenium. Because when this is spinning super, 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 super fast, electrons are hitting one point of it, but it's still spinning. It's still spinning, right? So electrons are going to interact with the tungsten and the rhenium. Everything else, this and this is molybdenum, as well as the stem. Okay? So
the focal track is made of tungsten?
Yes, with rhenium. So tungsten electrons will bombard with tungsten atoms. Make sense? So it's tungsten to tungsten. But you have tungsten and thorium on the cathode side, and you have tungsten and rhenium on the anode side.
Ms. Laura, I have a quick question. Where does graphite come in? I know the focal track. I get the molybdenum, but it also says graphite is like
There is a small base. I'm not sure if you can see it. It kind of sticks out right here. This is the back part with the stem. This is graphite.
Okay. Okay.
I know Ms. Bourne has kept this, and so I'm like, anode.
That's huge.
Yes.
Ms. Laura, so you said that tungsten will bombard the tungsten electron? Okay.
Yes. Okay, so if this tungsten, if we say this is tungsten, right? And we put this tungsten on the anode side, what is the filament made out of?
Tungsten.
Tungsten. So tungsten will collide with tungsten. Tungsten electrons will collide with the tungsten in the focal track. I'll say that specifically. The electrons that were boiled off will collide with the focal track, which is made of tungsten with a 2% of rhenium mix. Right? Good. And in the next chapter, we'll talk about what happens when these
We can't hear you, Miss Laura. We can't hear you.
We still can't hear you.
You're gonna have to hear me off my phone. I don't know why. Can you hear me now? Yes.
Yes, we can hear you.
Okay, awesome. So, what was I saying? Thank you. So, what was I saying about? I lost where I was. So, in the next chapter, we're going to talk about interactions, but not right now. Okay. So, what elements did we incorporate in this chapter? What elements did we talk about from the periodic table?
Molybdenum.
Molybdenum.
Rhenium.
Tungsten. Thorium.
Copper and nickel.
Nickel.
Copper.
Iron.
Don't forget the magnets. Glass. And then we've also talked about metal. Right? And lead. Where do we find lead?
In the protective housing.
Protective housing.
In the protective housing. Perfect. Good. So you guys are there. I like it. This was good. I like this. So remember what I said. You have to know your parts of your X-ray tube, or your whole X-ray, like the whole assembly. You have to also know your elements or your materials. And you have to know the processes. So what is happening? We're talking about electricity coming in at the cathode side and electricity coming in on the anode side. So know your phases, your mechanical phase or prep phase, number 1. And then you got to know your exposure phase, number 2. What is happening there? And it'll start to connect, I promise. So everything has a purpose. Down to the line focus principle. All of it has a reason. So make sure you understand if you know the reasons. If you don't know, ask me. Okay, that's the beauty about this program. You get tutoring with the teacher. Got it? So don't let that go by the wayside. Are there any other questions? No? I'm gonna linger for a little bit just in case.
I have a question. In the book it says, I think it's for whenever the second phase, I believe it is.
Mm-hmm.
It says the current heats the filament to a point of incandescence, or I don't know if I'm pronouncing that word right. White hot. I'm not comprehending that quite. Like,
so say it one more time. Say it again.
That the filament, that the current heats the filament to a certain point of incandescent, white hot.
Right. So what do we call that point? What are we expecting the filament to do, Amy?
To boil off the electrons, and that's
basically talking to that point.
Okay.
So it's getting so hot, white hot, that it is eventually going to start the thermionic emission of electrons.
Okay. Thank you.
You're very welcome. Okay.
I have one question.
Sure.
Talking about the anode heel effect and how the image gets lighter on the anode side, is it just because that there's not enough? There's not enough, or do they not have enough like penetrating power, and so they're just like getting absorbed like surface level, like on the skin?
I don't know. Okay, first I think I want to make sure that I understand what you're saying. When you say lighter, What does that mean? Lighter as in like brightness, or lighter meaning less photons in that side?
I guess I'm confused on which one it is, because I believe I remember it saying that the anode, or when we talked about the anode Hill effect, it makes the anode side lighter. Is that correct?
It makes the anode side lesser.
Oh, just lesser.
Use the word lighter. It's almost confusing to say, is the image going to be bright on that side? Not necessarily true.
Okay.
It is less. It means it is less. You have less photon quantity on this side, and you have more photons on this side. So which side of the beam will have more of a photon count? If you had to count them, you would have more photons on the cathode side than the anode side. So that is intensity. Intensity means how many photons are on this or in this beam or make up the beam. Make sense?
Yeah.
Good.
So, like, if you just did, just like, the abdomen, and you had one side is the cathode side of the abdomen gets hit by the cathode side, and it also gets hit by the anode side.
Right.
What would the anode side image look like for the for the abdomen compared to the cathode side?
I guess because I can't really use the abdomen as a point of reference because the tissue, okay, so the whole purpose of the anode and the anode Hill effect is to say that you would put thinner tissue that you would easily penetrate versus tissue that you could not easily penetrate, because you have more soldiers on the cathode side than you do on the anode side. So if you were to say, what would the radiograph look like? It's almost inaccurate because you have to accommodate the controls, meaning you have to generate as many photons as you need to get an optimal image. But if you were just to say, okay, well, nothing else, would this side of the radiograph be lighter? If nothing was in its way, yes. If that makes any sense. Only because you have more bombardment of this side of the beam with the image receptor. Because you have more photons interacting with the image receptor.
Okay.
Okay?
Yeah, okay. Thank you.
But that's not that. I don't want you to go into the future saying that the anode Hill effect is going to affect my image brightness, because it doesn't. Okay? We just want you to think about how many photons on this side of the beam will interact with the image receptor, as opposed to how many photons on this side of the beam will interact with the image receptor. And in a blanket term, more photons interact with the image receptor on the cathode side than the anode side because of the Hill effect. Because of the absorption of the photons. Does that make sense?
Yes, it does.
Because when we start talking later in the image itself, I don't want you to hold on to that and say, well, you told me the anode Hill effect is going to make it bright. No. We're talking about intensity. Less photons on this side, less interactions at the image receptor. More photons on this side, more photon interactions at the image receptor, period. Okay?
Okay, I got it now. Thank you.
You're welcome.
Ms. Laura, are we still going to go over the quality control and extending tube life? Or
yes, actually, there's only a few parts of the quality control. I don't want you to get into heat units. We're going to have plenty of time to get into heat units later. Don't go into heat units. I really want you to pay attention. This is it. This slide right here. Frequent use of high or maximum exposure factors. What are exposure factors eventually going to be? KZP, MA, and time. When we use an abundance of those factors, we can decrease the tube life expectancy, right? It's just like anything else. Overuse decreases its lifespan, right? So anything that's overused is going to decrease. If we keep heating that filament to its maximum use all the time, we are going to lower the life expectancy of that filament. Make sense? Perfect. So in the long run, it's going to ask us to use lower exposures. We don't want to overload the filament. There are many more factors in extending the tube life, but I promise you, ladies and gentlemen, we will have 3 more semesters of this that we're going to spend time talking about it. Got it? So I don't want to overload you right now. Get it? I want your expectancy in the program to last. No? Okay. Anyways, that's my joke for the day. And so I don't really need you to go further into that. Any questions? You don't know what lower but long. We're going to get to that when we start talking and incorporating exposure factors. Okay? Any other questions? No? Stop my sharing. Okay, let me get you back on my screen. All right, so nothing else? You guys are good? Feeling better? Ready?
Ready is a strong word.
Know your elements, know your materials, okay? And your phases. They're there for a reason, to start connecting the process of what happens in the X-ray tube. Okay, well, you guys have a great one. I'll see y'all later.
Thank you, Ms.
Nothing else for me. Bye.